Hello students, in this video we will be seeing about previous year question papers of NEET physics, and particularly we will be focusing on the topic called magnetism. So, we will try to solve some of the previous year question papers in which magnetism questions were coming for the past 10 or 15 years. So, before going inside the questions, let us have a statistical analysis report about magnetism topic. So, if you see magnetism topic, we have several subtopics inside. Around 30% of questions were coming from torque on a bar magnet, and 38% of questions were coming from magnetic properties of materials, and 13% of questions were coming from bar magnet and Earth's magnetism. So, this was the scenario for the last 33 years. So, majority of questions were coming from magnetic properties of materials and torque on a bar magnet, and very least percentage of questions were coming from current loop as a magnetic dipole and electromagnet and permanent magnets. But if you see the scenario for the last 8 years, more questions were coming from the bar magnet, and there was no questions from current loop as a magnetic dipole and electromagnet and permanent magnet. And the majority of questions were coming from these three topics: the bar magnet, Earth's magnetism, and magnetic properties of materials. So, around 30% of questions were coming from these three topics, and around 10% of questions were coming from torque on a bar magnet. Okay. So, we will try to solve some of the previous year question papers like covering all these subtopics one by one. The first question is, for protecting sensitive equipment from the external magnetic field, it should be. So, like they are asking you how to protect sensitive equipment from an external magnetic field, and they have given you options, 4 options, like surrounded with fine copper sheet, placed inside an iron can, wrapped with insulation around it when passing current through it, placed inside an aluminum can. So, usually what happens is when you have to protect the material, material from external magnetic field, it should be placed inside a iron core. Okay. So, it should be placed inside an iron core which will be acting as a magnetic shielding. So, the correct answer is option number B, placed in a iron can. Okay. So, this will behave like a magnetic shielding, and which will protect the material from the external magnetic field. Okay, it is a very simple direct question. The next question is, following figures show the arrangements of bar magnets in different configurations. Each magnet has magnetic dipole moment M. Which configuration has highest net magnetic dipole moment? Okay. So, they have given us 4 different configurations, and they want us to find out which configuration has the highest net magnetic dipole moment. Okay. So, they have placed the bar magnets in different configurations. Okay. So, one by one we will try to calculate. So, for the first configuration A, if you see, you are having it like this. So, this will be M is equal to M root 2. Okay. Next, for configuration B, you are having it like this. So, both are in opposite directions. So, the net magnetic dipole moment will be 0. So, they will cancel with each other. So, the net magnetic dipole moment will be 0. And next we will go with the configuration C. So, if you see in configuration C, you are having it like this. M. Okay. So, you are going to use this law of parallelogram of vectors. So, the net magnetic dipole moment is given by M is equal to root of M square plus plus 2M into m into cos 30 degree. Okay. So when you solve this, you will be getting it as root of 2m square plus 2m square cos 30 degree. Okay, this is 2m. So when you solve this, you will be getting the value of magnetic moment as m into root of 2 plus root 3. Okay, so this is for the configuration C, and the next configuration is D. So the only difference between configuration C and D is the angle. So here the angle is 60 degree, there it is 30 degree, and here it is 60 degree. Okay, little bit higher angle, and same way you are using this parallelogram law of parallelogram of vectors. You will be getting the value as root of 2m square plus 2m square cos 60 degree. So if you solve this, you will be getting it as m root 3. Okay. So when you compare all the four configurations, so for configuration A, you can see it is m root 2, and for configuration B it is 0, and for configuration C it is m root of 2 plus root of 3, and for configuration D it is m root 3. So in this four configuration, we can easily say that configuration 3 has the maximum net magnetic dipole moment. So the correct answer is option number C. Okay, so the configuration C is only having the highest magnetic dipole moment, net magnetic dipole moment. Okay, so this question will be it's a simple question only, since I have taken a longer time to explain it step by step. So when you know the concept easily, you can solve it within a few minutes. Okay, let us now see the next question. A wire of length L meter carrying a current of ampere is bent in the form of a circle. Its magnetic moment is. So here length of the wire L is equal to 2 pi r, and radius will be given by, radius of the loop is L by 2 pi. Okay, because the wire of length is only being converted in the form of a circle. Okay, so magnetic moment M is equal to I into A, and you know area of the circle will be pi r square. So A will be pi into L by 4 pi square. Okay, L square by 4 pi square. So your magnetic moment will be I L square by 4 pi ampere meter square. Okay, so the correct answer is option number A, I L square by 4 pi ampere meter square. Okay, so that is the magnetic moment of a wire of length L, which is being converted or which is being bent in the form of a circle. Okay, let us now see the next question. A charged particle, charge Q, is moving in a circle of radius r with uniform speed v. The associated magnetic moment M is given by. Here the magnetic dipole moment M is equal to I into A. So which is Q by T into pi r square. Okay, so since T is equal to 2 pi r by V, you will be having it as Q by 2 pi r by V into pi r square. So M will be Q V r by 2. Okay, here the r they have given it as radius capital R. So M will be Q V r by 2. So the correct answer is option number D, So the associated magnetic moment is given by QVR by 2. Okay. Let us now go on with the next question. A bar magnet is hung by a thin cotton thread in a uniform horizontal magnetic field and is in equilibrium state. The energy required to rotate it by 60 degrees is W. Now, the torque required to keep the magnet in this position is. So, here they are saying that a bar magnet is hung by a thin cotton thread in a uniform magnetic field and is in equilibrium state, and the energy required to rotate is 60 degrees is W. Now, how much torque is required to keep the magnet in its new position? Okay. So, W is equal to minus MB cos 60 degree minus cos 0 degree. So, it is minus MB cos 60 is 1 by 2 minus 1. So, this will be 1 by 2 MB. Okay. And MB is equal to 2W. So, torque required is equal to MB sin theta. So, which is equal to MB sin theta, which is equal to 2W sin 60 degree. So, torque will be 2W into sin 60 is root 3 by 2. So, it is root 3 W. So, the torque required to keep the magnet in its new position is root 3 W. So, the correct answer is option number C. Okay. So, we are just making use of this work done. W is equal to minus MB cos 60 degree minus cos 0 degree. So, MB into half minus 1 equal to half MB, and MB is equal to 2W, and you are taking the torque MB sin theta, you are just substituting it. Okay, because half MB is equal to W and MB is equal to 2W. That is what you are substituting here. Okay, let us now move on to the next question. A magnetic needle suspended parallel to a magnetic field requires root 3 joules of work to turn it through 60 degree. The torque needed to maintain the needle in this position will be. Okay, so work done to turn the magnetic needle, W is equal to MB cos theta 1 minus cos theta 2. Okay, and here theta 1 is 0 degree and theta 2 is 60 degree. So, MB cos 0 degree minus cos 60 degree is equal to root 3. MB 1 minus 1 by 2 is equal to root 3. MB is equal to 2 root 3. Okay. So, like this you are just first calculating the MB value. Now, torque needed to maintain the position of the needle will be torque equal to MB sin theta. So, which is equal to 2 root 3 into sin 60 degree. So, if you just substitute the formula, 2 root 3 by 2 equal to 2 and 2 will get cancelled, you will be getting 3 joules. So, the torque needed to maintain the needle in the particular position is 3 joules. So, the correct answer is option number B. Okay. So, we are making use of the work done to turn the magnetic needle, and with the angles 0 and 60 degrees you are substituting and you are finding it finding out the torque required. Okay. So let us now move on to the next question. A short bar magnet of magnetic moment 0.4 joule Tesla inverse is placed in an uniform magnetic field of 0.16 Tesla. The magnet is in stable equilibrium when the potential energy is. So here the potential energy U is equal to minus mb cos theta. So the magnet is in stable equilibrium when U is minimum, that is theta is equal to 0. Okay, so during that point the magnet is in stable position. So what happens is, if theta equal to 0, U will become minus mb. Okay, so here they are given you the value of magnetic moment as 0.4 into the magnetic field as 0.16. So if you solve this, you will be getting it as minus 0.064 joule. So the correct answer is option number B, minus 0.064 joule. Okay, it's a direct substitution of the formula. So let us now go on with the next question. A vibration magnetometer placed in magnetic meridian has a small bar magnet. The magnet executes oscillations with a time period of 2 seconds in Earth's horizontal magnetic field of 24 microtesla. When a horizontal field of 18 microtesla is produced opposite to the Earth's field by placing a current carrying wire, the new time period of magnet will be. Okay, so here the time period of the magnet T is equal to 2 pi to root of I by mb. As here the magnet used in both the cases are same, I and B remains constant. So T will be inversely proportional to the square root of the magnetic field. Okay, because I and B are constant, because we are using the same magnet. So Earth's horizontal magnetic field B1 is equal to 24 microtesla. So when a horizontal field opposite to the Earth's field is produced, what happens is B2 is equal to 24 minus 18, so which is around 6 microtesla. Okay, so you know that T is inversely proportional to the square root of B. So T2 by T1 will be equal to square root of B1 by B2. Okay, so if you solve this, you will be getting it as B1 is 24 and B2 is 6. So it will be root 4 and which is equal to 2. So T2 by T1 is equal to 2 and T2 is 2T1, and here they are given you the time period as 2 seconds. So T2 will be 4 seconds. Okay, because 2 into T1, so it will be 4 seconds. So the correct answer is option number D, 4 seconds. Okay, let us now move on to the next question. The relations among the three elements of Earth's magnetic field, namely horizontal component H, vertical component V and dip R. Okay, so here the relation is V is equal to B sin del. This is the relation between the vertical component and horizontal component will be B cos del. Okay, so the correct answer is option number C. Okay, it's a direct formula based question where the relationship between the vertical component and the horizontal component with the dip del is given by vertical component is B sin del and horizontal component is B cos del. Okay, so let us now move on to the next question. At a point A on the Earth's surface, the angle of dip del is equal to plus 25 degree, and at a point B of the earth surface the angle of dip is minus 25 degree. Okay, we can interrupt that A is located in the northern hemisphere and B is located in the southern hemisphere. A and B are both located in the southern hemisphere. A and B are both located in the northern hemisphere, and A is located in the southern hemisphere and B is located in the northern hemisphere. Okay. So here angle of dip is the angle between the horizontal component of Earth's magnetic field and the total Earth's magnetic field. Okay. So here at equator the dip will be 0 degree and the magnetic dipole at the magnetic poles it will be 90 degree. Okay. So del is negative in northern hemisphere and positive in southern hemisphere. Okay. So del is negative in the northern hemisphere and positive in the southern hemisphere. So here you can see del value is positive. Okay. So positive means it is in the southern hemisphere, and here it is negative. Negative means it is in the northern hemisphere. So A is located in the southern hemisphere and B is located in the northern hemisphere is the correct answer. Angle of dip is the angle between the horizontal component of Earth's magnetic field and the total Earth's magnetic field. So at equator it will be 0 degree and at magnetic poles it will be 90 degree. So you can see that del is negative in northern hemisphere and positive in southern hemisphere. So the correct answer is option number D. Since A is positive, so it is located in southern hemisphere, and B is negative, the angle of dip of B is negative, so it is located in the northern hemisphere. So the correct answer is option number D. Let us see the next question. If theta 1 and theta 2 be the apparent angles of dip observed in two vertical planes at right angles to each other, then the true angle of dip theta is given by. Okay, so here they are telling that theta 1 and theta 2 are the observed angles of dip in two mutually perpendicular planes, and theta is the true value of dip. Okay, so in that case what happens is tan theta 1 is equal to BV by BH1. So similarly tan theta 2 is equal to BV by BH2. So tan theta will be BV by BH. So as here you can see BH1 and BH2 are the horizontal components in two vertical planes perpendicular to each other. So you will be having B square H is equal to B square H1 plus B square H2. So we know that what is BH is? BH is tan theta BV by tan theta. Okay, so just you are taking this side. So BH square will be BV by tan theta the whole square equal to, similarly here BH1 is BV by tan theta 1 the whole square plus BV by tan theta 2 the whole square. Okay, so all the BV's will get cancelled with each other like this, and you know tan theta 1 by tan theta is cot square theta. Okay, cot theta, so it is already square is there, so cot square theta is equal to cot square T1 plus cot square T2. Okay, so the true angle of dip is given by cot square theta is equal to cot square theta 1 plus cot square theta 2. So the correct answer is option number A. Okay. So here we are making use of the theta 1 and theta 2, which is the observed angles of the dip in two mutually perpendicular planes. So where theta is the true value of the dip. So in that case we will be having tan theta 1 is equal to BV by BH1 and tan theta 2 equal to BV by BH2. So, you are just substituting it and you are finding out the true angle of tip. Okay. So, let us now move on to the next question. A compass needle which is allowed to move in a horizontal plane is taken into a geomagnetic pole. It will become rigid, showing no movement. It will stay in any position. It will stay in north to south direction only. It will stay in east to west direction only. So, here what happens is the horizontal component of Earth's magnetic field will become 0 at the geomagnetic pole. So, the compass needle will always stay in any position. Okay. So, it will stay in any position when the horizontal component of the Earth's magnetic field becoming 0 at the geomagnetic pole. So, what happens is it can stay at any position, the compass needle will stay in any position. So, the correct answer is option number B, will stay in any positions. Okay. Let us now move on to the next question. A iron rod of susceptibility 599 is subjected to a magnetizing field of 1200 ampere per meter. The permeability of the material of the rod is. So, here they have given you the mu naught value as 4 pi into 10 power minus 7. So, the relative permeability mu r is equal to 1 plus psi. Okay, and they are giving you the susceptibility value as 599. So, this will be 1 plus 599 which is equal to 600, and the magnetic permeability mu is equal to mu r into mu naught. So, you know what is mu r is 600 into mu naught value, they are given it as 4 pi into 10 power minus 7. So, when you solve this you will be getting it as 2.4 pi 10 power minus 4 Tesla meter per ampere. Okay. So, the correct answer is 2.4 pi into 10 power minus 4, option number D. So, it is just a direct substitution of the formula. First, you are finding out the relative magnetic permeability, okay, which is mu r equal to 1 plus psi, and psi value they are given it as 599, you are substituting, and then you are calculating the magnetic permeability which is equal to mu r into mu naught. So, you know what is mu r, you are substituting, mu naught they are given in the question, just you are substituting and you are finding out the permeability of the material which is 2.4 pi into 10 power minus 4. Okay, it is a very simple question, direct application of the formula. Let us move on to the next question. The magnetic susceptibility is negative for ferromagnetic material only, paramagnetic and ferromagnetic materials, diamagnetic material only, and paramagnetic material. Okay. So, if you see the magnetic susceptibility for diamagnetic material, okay. So, actually first you should know what is magnetic susceptibility is. It is a dimensionless proportionality constant that indicates the degree of magnetization of a material for a applied magnetic field. Okay. So, if you see here the susceptibility is given psi equal to m by b. Okay. So, where m is the magnetization of the material and b is the applied magnetic field. So, in the case of diamagnetic material, psi will be equal to minus 1. Okay. So, it will be having a negative value, but in the case of ferromagnetic or a paramagnetic material, it will be having a positive value. Okay. So, the correct answer is diamagnetic material only. It is a simple question. Psi will be equal to minus 1. Okay, where m is the applied magnetic magnetization of the material and b is the applied magnetic field. So, diamagnetic material will not have any kinds of response for any applied magnetic field. So, that is why the susceptibility value will be negative. So, the correct answer is option number C. Okay, let us move on to the next question. The magnetic moment of a diamagnetic atom is. So, the magnetic moment of a diamagnetic atom will be what? It will be greater than 1, or it will be 1, or it is between 0 and 1, or it is equal to 0. Okay. So, they have given us 4 options. So, the magnetic moment of a diamagnetic atom, whether it will be 0 or 1, or whether it is between 0 and 1, or it is greater than 1, or it is 1, or it is equal to 0. Okay. So, if you see here, the correct answer is option number D. The magnetic moment of a diamagnetic atom will be 0. It's a simple question. As I was saying you, the magnetic moment will be 0 because atoms have paired electrons. So, you know that the contribution for a magnetic property of a material is the unpaired electrons. So, if you see in ferromagnetic materials, we will be having more unpaired electrons like this, and in paramagnet you will be having less unpaired electrons, and these unpaired electrons will contribute to the magnetic moment of a material. But in the case of diamagnetic material, what we will have is it will be having more paired electrons. So, more paired electrons will be present in the case of a diamagnetic material, and the spins will cancel with each other. So, automatically what will happen is the net magnetic moment is 0. So, that is why if you see the magnetic moment of a diamagnetic material will be 0. So, that like the electron in an atom revolving in an orbit around the nucleus, and the revolving loop is equivalent to a tiny loop of current. We know that because of that only we are having a magnetic moment. Okay. So, it is like an electron revolving around the nucleus, and when you are having more like this, when this it's similar to a current flowing in a tiny circuit, and we know that if a current is flowing in a circular loop in a perpendicular direction, magnetic field will be produced. Okay. So, here what happens is since more number of paired electrons are there, they will cancel with each other, and the net magnetic moment will be 0. So, the correct answer is option number D. Okay. Let us move on to the next question. If a diamagnetic substance is brought near north or south pole of a bar magnet, it is attracted by the poles, repelled by the poles, repelled by the north pole, and attracted by the south pole, attracted by the north pole and repelled by the south pole. Okay. So, we all know that the diamagnetic substances will be having a negative intensity of magnetization. So, they will be weakly repelling to the external magnetic field. Okay. So, as we saw in the previous questions also, the susceptibility value is in negative. Okay. So, even if you apply a large amount of magnetic field also, the material does not get magnetized. So, the correct answer for this is it is repelled by the poles. So, the option number B is the correct answer. Okay. Due to the negative intensity of magnetization, the material will be repelling to the magnetic field applied on it. Okay. So, option number B is the correct answer. Okay. Let us move on to the next question. Curie temperature above which paramagnetic material becomes ferromagnet, and ferromagnetic material becomes diamagnet, and ferromagnetic material becomes paramagnet, and paramagnetic material becomes diamagnetic material. Okay. So, first we should know what is a Curie temperature is. So, Curie point is also called as Curie temperature, at which certain materials undergo a sharp change in their magnetic properties. Okay. So, for example, when you are plotting a graph between the susceptibility and temperature, we know that at some point you will be having a kind of a transition. Okay. It is just a simple example, maybe not exactly like this, maybe like this, some kind of a transition taking place. So this point maybe we can say it's a Curie point or a Curie temperature. Okay, so not exactly there, over here, like here, this we can say it as a Curie point or Curie temperature, where there is a transition from ferromagnet to paramagnet. Okay, so in this temperature the materials undergo a sharp change in their magnetic properties. So the material might be a magnetic material, and it can be a ferromagnetic material, and at this point you can see it gets transferred to a paramagnetic material. Okay, so that's what happens. So above the Curie temperature, the ferromagnetic material becomes paramagnet. So the correct answer is option number C. Okay, so below the Curie temperature, the material will behave like a paramagnet. So you can remember this graph, it will be easy for you for your understanding. So this is magnetization versus temperature, and you will have the area. In this area the material will be ferromagnet, and above this it will be paramagnet, and this is the Curie temperature. Okay, so easily you can know that above Curie temperature the material becomes, ferromagnetic material becomes to paramagnet. So if you remember this graph, you can easily answer this question. So the correct answer is option number C. Okay, let us move on to the next question. Nickel shows ferromagnetic property at room temperature. If the temperature is increased beyond Curie temperature, then it will show antiferromagnetism, no magnetic property, diamagnetism, and paramagnetism. Okay, so here they are given you 4 options where they are saying that it is showing ferromagnetism at the room temperature, and if the temperature is increased beyond Curie temperature, what will happen? So it's a similar question like the previous one, where we showed that the material above Curie temperature, it will become like a paramagnet. And here nickel exhibits ferromagnetism due to some kind of a quantum physical effect called exchange coupling, in which the electron spins of one atom interact with those of the neighboring atoms. So if the temperature of the ferromagnetic material is raised above certain value, what happens is the coupling ceases to be effective. So most of the such materials will become like a paramagnet. So the correct answer is option number D. Nickel will behave like a paramagnet. Okay, let us move on to the next question. If the magnetic dipole moment of an atom of a diamagnetic material, paramagnetic material and ferromagnetic material is denoted by mu d, mu f, mu p and mu f respectively, then they have given you 4 options. Mu d is not equal to 0, mu f is not equal to 0, mu p equal to 0, mu f is not equal to 0, mu d equal to 0, mu p is not equal to 0, and mu d is not equal to 0 and mu p equal to 0. Okay. So here they have given you 4 options. And as I was saying you about the spin of electrons. Okay. So in the case of diamagnetic material, you will be having the pairing of electrons like this, and in the case of paramagnetic material you will be having the pairing of electrons like this, and in the case of ferromagnetic material you will be having more number of unpaired electrons. So this is in the case of dia, this is in the case of para, and this is in the case of ferro. Okay. So here they are telling that the magnetic moment mu d is for dia and mu p is for para and mu f is for ferro. Okay, it's a very simple question. First you check the first option, mu d is not equal to 0. So mu d is not equal to 0 means it's wrong, because we know that the net magnetic moment of diamagnetic material will be 0. Okay, because all the pair of electrons, the spins will cancel with each other and you will be having a net magnetic moment as 0. So the net magnetic dipole moment will be 0 for dia. So we have only one option where mu d equal to 0 and mu p is not equal to 0. So it's correct, because paramagnetic material will be having a feasible magnetic moment. So it cannot be 0. So the correct answer is option number C. Mu d equal to 0 and mu p is not equal to 0. Okay. So that is the correct answer. The next question is, electromagnets are made of soft iron because soft iron has low retentivity, high coercive force, high retentivity and high coercive force, low retentivity and low coercive force, high retentivity and low coercive force. Okay. So first we should have an idea about hysteresis curve. So you know that hysteresis curve gives you a relationship between the applied magnetic field and the magnetization of the material. So initially when you are applying a magnetic field, the magnetization of the material will increase and it will reach a point called saturation. So even if you apply a large magnetic field beyond this point, the material magnetization will not increase. Okay, so that point we call it as saturation. And when you are removing the applied magnetic field, it will not come back to 0. The magnetization does not come back to 0, but it goes to another, it takes another path and it will have some residual magnetism in the material, even the applied magnetic field is 0. So that we call it as retentivity. So this is determines the magnetism left in the material, even the magnetizing field has been switched off. So here in electromagnets which are operated in a condition requiring fast reversal of polarity, so high retentivity is undesirable. In electromagnets you cannot have a high retentivity which is undesirable, and susceptibility determines to what extent the material responds to the applied magnetic field. Okay. So this means it determines the extent of which the material will get magnetized when the given field of strength is applied. Okay. So electromagnets must be made of materials which are having high susceptibility. That is, when you are applying a magnetic field, the material has to get magnetized at a faster rate. So high susceptibility, and they should also have a low retentivity. So low retentivity means, so here they are asking it is soft iron. Okay, soft iron. So these electromagnets which are made of soft iron should be having a low retentivity and a low coercive field. So the correct answer is option number C. So when they are having a, because the electromagnets will be operated in condition which requires a fast reversal of polarity. So if you are having a high retentivity, then the material it will not be like it will be undesirable for its operation. So it should have a low retentivity rate. And coercive field means the reverse field which you are going to apply to bring back the residual magnetism to 0. So since we are having a low retentivity, the coercive field also will be low. So that's why the correct answer is option number C, low retentivity and low coercive force. Okay. So I think this video would have been useful for you to understand the basic concepts of the unit called magnetism. And as I was saying you in my previous slide, the initial slides, if you just have a look, the majority of questions were coming from topics like bar magnet and Earth's magnetism and magnetic properties of material. So try to concentrate on these three topics particularly and try to solve problems related to these three topics, because 90% of questions were coming from these three topics in the last 8 years. So I wish you all a good luck for your examination, all the best, and prepare well for the exam. Thank you for watching this video.